Continuing in 1.6, let's look at definition 1.17, basis for a subspace. So concept of basis is what we're really focusing on here. And so let's let W be a subspace of Rn. And let's suppose we have W sub i's be the vectors in W. Okay, so then the set W1 to W sub k, so we're basically saying I runs from 1 to k. So that set is called a basis, or is a basis for the set W, for the subspace W, if every vector in W can be expressed uniquely as a linear combination of W1 through W sub k. So if every vector in W, so picture a bunch, picture R2 or something, all those vectors in W can be uniquely expressed as a linear combination of those vectors. So of W1 to WK. Oops. Getting ahead of myself there. So I think you want to focus mostly on that so there exists linear combinations of W1 through WK that create the set W. So every vector in W can be expressed as a linear combination of these guys. And then they're unique, but that's just kind of comes with the linear combination. It's like you have another one. So focus on that this set creates this set by linear combinations. Now, this is slightly different than span. So we already know a span is a subspace. So they're connected, but it doesn't have to just be a span. Remember, a span is just all possible linear combinations of those vectors. So in this case, it's just saying that every vector in the set or the subspace can be basically created by all these vectors. And then we have our standard basis. So the standard basis vectors look like this. Standard basis we use the E, right? E1 through En. So this is the standard basis. And then, so that's that'll create that's the substandard basis for Rn. So every vector in Rn can be created by linear combinations of these. So that's the standard basis, and then we've studied in the past, or you have I, j, and k, which is E1, E2, E3. That's the standard basis for R3. All of R3. So if you just had a set, a different type of set W, then it's a basis if this holds. So that's the definition, and then we can come up with other properties and concepts as we go. Let's look at theorem 1.15. We're going to roll off a number of theorems and concepts before we hit an example. It's kind of the nature of this section. But let's do the next theorem. This is theorem 1.15. This is regarding the unique linear combination. This is an interesting result, I think. So theorem 1.15. This is on unique linear combination. So you could think of this as a result of this definition. How can you use that to describe a subspace or a basis? I'm sorry. How can you use that definition to describe a basis for a subspace? So this is what we have.